question, feel free to let me know. Okay. So, what do you know about the integral? Have you ever heard or have you used before the integral? Anyone? Do you use integral before during your secondary school? During your matrix or any time?
Yes.
Okay, what?
Integration.
Yes. What do you actually solve using the integration? You solve for? There are many things you solve. For example, you solve for differentiation, right? And then you solve for the gradient.
Volume.
Yes, the volume, the area. So basically, the integral form is used to solve the solution. Okay, so now in the fluid mechanics, we need the integral form to solve the fluid mechanics problem. Alright, so in the fluid mechanics problem, we can view it as a differential form. Alright, for example, like the particle, the very small particle, the finite volume method, or any kinds of motion, any kinds of area, we can solve using the integral form. Alright, so the integral form is very important to solve, especially when we have the different kinds of area. Alright, for example, area inlet 1 different with area inlet 2. So two options. Yeah, let me connect first my this one. Okay. So two options for studying the fluid flow. Alright. First, can study the motion of individual fluid particle. This is what you know. Individual. What do you know? Have we learned before?
Lagrangian.
Yes, perfect. Like Lagrangian flow description. Alright. Lagrangian description. Yes, you still remember. Okay, thank you. So, can study the region of space of the fluid flow through. This is the?
Eulerian.
Yes, perfect. Eulerian. Remember that the Lagrangian involve only the time. Okay, only the time with the function of time. However, for the Eulerian, it is function of space and time. Okay, normally space we put it this way: x, y, z. This is space and time. Alright, so we will look at this one in this chapter. Alright, so we will review the physical law as they apply to the system. Okay, go over maths needed to convert from the system to the control volume. Obtain formula for the physical laws by combining the result. So basically, this chapter involves of converting from the system into the control volume. Alright, so how do we convert from the system into the control volume? Alright, we're going to use the integral form. Okay, so normally we learn about the basic law. Alright, for example, the basic law that we learned previously, the conservation of mass. Alright, so what the conservation of mass? The conservation of mass is the mass of a system is conserved. Right? Conserved and doesn't change, right, with time. That means there is no change of mass property over time. For example, this is the right, like this is the empty bottle, and there is the flow from inlet to outlet. The mass here, alright, still the same amount of mass over time. Alright, so from here, the mass of the system is constant. Alright, so we can put this way: the differentiation of mass over time equal to 0. Alright, that means it is under steady state. This is what the conservation of mass. The mass of the system is conserved. You need to remember this. Alright, and then we learned about the Newton's second law. So what is the Newton's second law? F equal to mass multiplied with acceleration. This is vector, this is vector. Alright, so if there is a net force, which is F, on the system, the mass in the system will accelerate. Very simple. When there is the net force, it is not equal to 0. Yeah, there is the value. Then the mass of this system will accelerate. You can see the mass of the system will accelerate. So the summation of force, okay, the sum of force equal to the time rate of change of linear momentum. Okay, this is point number 1, this is point number 2. So what it means, you can see summation of force equal to mass multiplied with acceleration. Okay, so we know already that acceleration is the function of velocity over time. So we can convert this one d over dt, and this one mass, this is velocity. You can see velocity over time is acceleration, this is mass. Alright, this mv here represent the momentum. Time rate refer to dt. Alright, so far you have any question pertaining to the Newton's second law and conservation of mass? Is it easy for you? Clear so far? What's the conservation of mass? Alright, just repetitions. The conservation of mass is the mass of the system is conserved. dm over dt equal to 0. For the Newton's second law, alright, if there is a net force, the mass in the system will accelerate. So summation of force equal to ma. So this acceleration we convert into velocity over time. So mass multiplied with velocity is momentum. So time rate of change of linear momentum. Okay, so how about the angular momentum? What do you know about angular momentum? Angular is rotation. Okay, so the rate of change of angular, or you can say rotation, momentum is equal to the summation of all moment acting on the system. Alright, so this is the formula. Okay, M, alright, angular momentum equal to dH. This is the vector over dt. Alright, so where H is equal to summations of R cross product with velocity multiply with the small change of mass. Okay, it is like V equal to R omega. Okay, this is R multiplied with V multiplied with the small change of M. So we got the H. Okay, so and then finally it is the first law of thermodynamic. Okay, if heat, okay, the change of heat Q is added to the system, okay, to the system, okay, the work, the change of work is done by the system. Therefore, dE, the change of energy, must change. This is the definition of a first law of thermodynamic, where the change of Q, okay, added to the system, and then the work done is done by the system. This is negative. Work done equal to dE. Alright, this is system energy. Alright, so simply we can put this way. Alright, so this is the small change of Q added to the system and the work done by the system. So the system do the work, so it is negative here, equal to the change of energy. So all this term we can actually divide with the time rate dt in order to get the rates of change. So when we divide all this term with dt, we're going to have this equation, Q dot. Alright, what is Q dot? Anything divided with time, we will have the dot. Alright, minus W dot equal to dE over dt. Okay, so this is the law of thermodynamic. So now we proceed to the control volume. So why we use the control volume? So what do you know about the control volume? What's your expectations of control volume? Anyone? What do you know about control volume? What's the property of control volume? Have you ever heard about control volume?
Then mass.
Yes, and thermodynamics.
Yes, you learn about thermodynamic. You have the thermodynamic 1 and 2 or only 1?
No, only one.
I see. Okay, what do you learn about during thermodynamic for the control volume?
The volume doesn't change, as I remember.
Yes, perfect.
Doesn't change within time. So it's a steady flow.
Okay.
Or is it a closed system, I guess?
Alright. So basically, control volume is the region, the fixed region, Alright, it is not change position. It is only, we focus only one position. So that is what we call the control volume. Okay, so from here, we use the control volume. Alright, the equation above are written for the system. Okay, so by using the control volume, we can look at, for example, alright, when we focus on the system alone, right, we can look at how beam deflect under load. Alright, and second one, maybe this is just example, yeah, can study the position. Okay, can study the position of piston oscillate. Okay, this is inside the automotive car. Alright, so in fluid mechanic, by the way, fluids, alright, fluid is a cair, something that move, alright, like water, like air, often alter the environment. For example, when we have the mechanism inside the water, so that mechanism surrounded by the fluid, so it will alter the surrounding. For example, we have the piston. When we do something, it will increase the suction of air, so it will alter the system. So it is very related to the system and the fluid mechanic. Alright, environment in which on product operate. Whatever product or machine operate, it will alter the environment by the fluid mechanic, by the fluid itself. So that is why we need to know the effect. Okay, so for example, winds loads on beam. Alright, so can you give example winds loads on beam? Anyone? Do you have ever counter this issue, the winds load on wing? For example, I give you the crane. Okay, we have the crane. I believe you know, yeah, the crane, the lifting crane. Okay, what do you think of the factor that affect the stability of the crane, the lifting crane? Anyone? What do you think of any factor that affect the stability of the wing? Of the crane. Definitely, it will involve the wind, right? The wind loads. All right. For example, okay, we have the wind direction from this. Okay, the wind direction hitting this. Okay, and then supposedly without the wind, the crane operator managed to lift this load. When there is the huge amounts of wind, definitely this crane will topple down. So that is why you can see the wind plays a very important in determining the stability of the crane. Okay, so that's why you must learn the fluid mechanic in order to study the effects of the wings acting on the beam. For example, this is the beam. Okay, and maybe for this one, second one, the drag and lift loads on rocket. Okay, this is what we study the rocket. So we need to study the drag force, right? The drag force, and then the lift force. So this is what involved of fluid mechanics. Okay. So from here we need the basic laws to be written. Okay, and to apply to a specific region in the area of the product. Alright, for example, the whole this image considered as the system. So for us to investigate the load here, we need to consider the control volume. That means we focus on this region. Okay, this is control volume. Alright, this is the whole system. Definitely it is impossible for us to analyze. Maybe we can analyze, it's going to take time to analyze the whole system. But in the fluid mechanics, we have the method to focus on specific region, we call as the control volume, to analyze the wings loads on the beam. Okay, so from the system, you can see the whole this is the system, and then we need to analyze only this region. We need the conversion from the system into the control volume. Okay, so how do we convert from the whole system into the control volume? We're going to use the Renault transport theorem. Okay, this is the Renault transport theorem. Okay, Renault transport theorem used to convert from the system to the control volume. Okay, so fluid system, specific mass of the fluid within the boundary defined as the closed system. Okay, the shape of the system may change with time. Okay, so the system, the shape of the system may change with time. However, for the control volume, it will be fixed at all time. Okay, so for example, here, fluid flowing through, right, constriction, right, for example, like the gas compression. Okay, this is how it looks like. Okay, right, can you see this is the constriction? It is narrowing down, and then we have the fluid flow. Okay, this is the compression. So the fluid flow, okay, the region of this is the fixed region we call as a control volume. Okay, the system is actually the whole of the system. It is a moving of the water from point here, point A, into point B. So you can see the shape of the system may change. However, for the control volume, it is fixed. This is fixed. Okay, As fluid move and deform, you can see as the fluid move from left to the right, it will deform. Alright, the system move and deform. This is the difference. Okay, like this. Okay, from here. Okay, this is the system, yeah. This is at time 1. And this is at time 2. And this is at time 3. Okay. Can you see this is the system? The fluid move and deform. This is system. However, this is for volume, control volume, where we focus only the specific region. Okay, we focus on this. Okay, it is always fixed. Okay, it is the space, it is the area that we focus on. For the system, it will deform. So the control volume, as I mentioned before, it is the fixed region in space. You can see this is the fixed region in space, which doesn't move or change shape. Okay, usually selected as the region that fluid flow into and out of system. So the closed boundary called the control surface. So this is the closing one, the closing boundary. Alright, here we call it as a control surface. Alright, this control surface, alright, close the boundary here. Right, you can see the dotted line. We can say it is a control surface. The control boundary dipanggil called the control surface. Okay, the shape of the control volume is optional. Alright, it depends on your problem or your case study. See, so for this one, okay, often choose boundary. Okay, this is the optional one. The control volume is optional. So how to choose? Often choose a boundary, alright, to coincide with some solid or natural flow boundary. Okay, so usually MAC boundary. Okay, this is the boundary that you decide on your own, perpendicular to the flow. Alright, for example, we have the box. Okay, and then we have the flow, for example, from here to here. So how do we choose the control surface or control volume? You can see this is horizontal, so this is perpendicular. Okay, inside here we can choose as the this is control volume. Outside here is a control surface. Okay, you need to know this because we're going to derive the Renault transport theorem. Okay, at time t, the control volume and fluid system coincide. Okay, this is at the initial time. So, what it means by, let me explain to you. For example, we have the diffuser. Okay. For example, we have the diffuser. Okay. Alright. So right, this is the fluid flow. Okay, right. Okay, this is the system. Okay, remember that the system, this is the fluid. Okay, this is the fluid system. Yeah, I said the fluid system. That means the whole this thing will move with respect to time. Okay, so from here we can also coincide with the control volume. Okay, you can see it is at the same position at initial time at t equal to 1. Alright, so at time t, that means at time 1, the control volume and the fluid system, you can see the fluid system and the control volume, the red color coincide. For example, this is point 1 and this is point 2. Okay, the flow from here, right, to here, it is initially coincide. What happened after a few times? Do you think coincide or no? And why? Do you guys think after at the time 2, what do you think? What happened to the fluid system compared to the control volume? Anyone would like to try? It's okay, just give your opinion. Do you have any idea? Don't worry. Definitely, it will. The fluid system will move. The control volume will be fixed because the control volume will be as the fixed region. Okay, the fixed region in space. So you can see during the change of time, maybe at time 2, the system move. Okay, however, the control volume fixed. Okay, let me draw this way. Okay. This is the diffuser, yeah. Alright, and this is the alright. Let's draw for the at time 1. So initially it is at this position. Okay. Initially it is at this position. This is for the system, yeah. Okay. And then this system will move here. So maybe this way. Can every one of you imagine what happened? Alright. Maybe I can try use a different color to make it different. Okay, this is initial. Different color, maybe orange. Okay, and then it will move in this position. Okay, this one. Okay, now can you see? Initially at time 1, at position here. Okay, this is at I. Okay, for example, this is region I, and this is region 2. Okay, so here this is the original control volume. Okay, the original control volume doesn't move. Doesn't move at all, for example. So let me put this way. I is a region uncovered. Okay, uncovered, not covered, during delta t, the change of time. Alright, can you see the orange color? It is moved, that means I is not covered, it is uncovered. Okay, this is at the time plus delta t. Okay, and however for the region 2, a new region. Can you see the new region? This is the region, only this region. Okay, new region. Okay, covered by fluid system. Okay, so this is not part of control volume. Alright, why not part? Because the control volume always fixed. Okay, it is not part of the control volume. Okay, the whole this thing is the system, but we consider the control volume in this region, the initial point. You see here. Alright, can you see the fluid system coincide with the control volume? Okay, after a few seconds, for example, as the delta t, the fluid of the system move from region I, region 1 into region 2. Okay, so from here, okay, at t plus delta t, the system has the same fluid, but it occupies the region. Okay, so can you see at t plus delta t, maybe at a few seconds, after a few time, this is the initial. Okay, this is after the time, the system has the same fluid. Alright, remember it is guided by the boundary condition. It is moved from one position to another, but it occupies the new region. So what's the new region? Okay, so this is the new region. Okay, it occupies the control volume. You can see this is control volume minus, can you see? You need to minus I. And after that, you need to plus I, double I. Do you get it, everyone? So far? How? Okay, this is the new region, yeah? The control volume, this one, minus I plus this one. Definitely, you're going to have this, the orange color. Everyone understand? This is the new region. Apply for new region. You guys there?
Yes, doctor. I understand.
Okay, you understand, yeah? Okay, so remember that, okay, this is the new region. This is the new region for the system. Okay, so from here, remember that the control volume is fixed. in space. So from here, let's say we put this way, the B. B may be any kinds of property like volume, velocity, temperature, any kinds of thing like B. Any kinds of property. B of the system. Okay. At time t is equal to the B of the system. Sorry, the B of the control volume at time t. Okay, this is what it means by coincide. You can see here, the B mean any property, the fluids, alright, maybe B is the fluid, the fluid of the system, you can see, coincide with the control volume, okay, at time t, the initial time. So after a few time, t plus delta t, we can put this way, B of the system at time t plus delta t equal to B of the control volume, okay, at time t. Just follow this one. This is new region, yeah. This is for the right side for control volume, the left side for the system. T plus delta t. Just follow this one, minus B control volume, sorry, B for the I, okay, I at time t plus delta t and plus B at I2 t plus delta t. Okay, you must be confused why we have all these equations, because I want to show you the derivations of Renault transport theorem in order to convert from the system to the control volume. Okay, so far you have any question pertaining to this?
Doctor?
Yes?
What does space stands for? B.
Space
No,
is the
I mean B.
the B any kinds of property like fluid, air. Okay.
Okay, doctor. Thank you.
Okay. So subtracting the first equation from the second one and dividing by delta t. Okay. So you need to, from the second equation, you need to minus with the first equation. Okay, let's say this is equation 1. Equation 1 and this is equation 2. So the question asks subtract 2 minus 1. Right? So B system, all this minus this one. Okay, I try to subtract B of the system. Okay, this is T plus delta T. This is from equation 2, yeah. Minus back this one. Like this, yeah. You make it like this. Minus. So you will have B of the system. You will have B of the system minus this one. Okay, B of the system minus B of the system at time 1. Okay, this is the change of time minus T. Okay, equal to, can you see this one? Control volume minus control volume. Okay, so B of control volume with respect to the change of delta T minus B control volume with T. All these must be divided with delta T. Sorry. And also this one, there is no any companion, any partner, just this one minus 0, this one minus 0. So we only have this one, negative. B, I, region I, T plus delta T, divide with delta T, plus B at region 2, at T plus delta T, divide with delta T. Okay, so taking the limit delta T equal to 0, this is approaching 0 in order to introduce the derivative. Alright, so we need to convert all these to derivative. Alright, instead of delta, we can use the derivative differentiation because we're going to integrate later on. So from this one, this is the change. Alright, the system, the change of the system. Delta T minus, this is T plus delta T minus T. So definitely the change of the system. So dB, can you see this is minus over with dt. Why we use the differentiation? Because we consider this the approach of delta T approaching 0. Okay, we can use the definition of derivative. So from here, you can see this is the change also, the change of control volume. So the change is B. B control volume over with dt. Minus, this is, there is no change at all. So this one, divide with time, we can put dot on top of B. Remember, anything divide with time, we will have the dot. This is, you can see this is I refer to in. Okay, because you can see here, this is the inlet and this is the outlet. So we can replace the we can replace the one, sorry, we can replace the I with in dot plus B out dot. Okay, this is the rate change of B. So here is the Renault, okay, Renault transport theorem. This is we call as a RTT. Alright. Okay. So letting here. Okay. A B equal to B over M. Remember that anything divide with M, the mass will be the small letter. For example, like the volume. Okay, the volume. When you divide the volume with mass, you will have the small v. I believe you learn, yeah, during the thermodynamic. Okay, anything divide with mass, it is small. Anything divide with time, it is, anything divide with time will have the, okay, anything divide with time. For example, this one divide with time will have the v dot. Okay, that is the concept lah. We need to know the concept of engineering. Okay, let's say B, small b is a capital B, capital B divide with mass. And B control volume is equal to rho, so the integral of rho B dV. Okay. Actually, can you Ibrahim, can you switch off your camera? Okay. So from here, let's proceed. So from here, all right. Okay. Y B equal to integral density B dV. Okay, we look at here. The density and V, you know density equal to mass over volume. When the density divide with the volume, you will have the mass. Okay, so the mass multiply with the B. Okay, mass multiply with B, you're going to have the capital B. Can you see here? Okay, it is the same thing. Okay, from here you can see it is actually rho dV. It is reflect to the change of mass. Okay, so from here, okay. So using again the equation here, can you see dB of the system over dt? Okay, B of the system over dt equal to, okay, can you see here? Okay, we introduce the d over dt integral. Basically, d dt with the integral, it is cancel each other. Okay, we will have the density multiplied with b dv. Okay, remember that rho b dv is this. It is b multiplied with the mass. Okay, minus with b in here. Okay, we can replace here with b1. b1 rho 1, velocity 1, area 1. Okay, plus b2 rho 2, v2 a2. This is how we change from this form into the integral form. Okay, you look at here. Basically, this form, the v rho, the velocity is a function of, okay, length divided with time, displacement divided with time, and the area is the length multiplied with the length. Okay, so here L multiplied with L multiplied with L is it is the volume. So volume divide with time, this is the volume over time multiply with the density. Okay, so here is the volume. Volume multiplied with density is the mass. Okay, mass multiplied with the B is the capital B. So capital B divide with time, the change of B, capital B. It is the same thing here. Okay, so from here, okay, this is what we explain. Okay, so above description, use one inlet and one outlet. All right, we have the inlet and outlet. So can generalize the theorem for multiple inlet and outlet. For example, we have multiple inlet and outlet. This is for one inlet and one outlet, point 1 and point 2. Maybe we will have different inlet. Okay, this is point 1, point 2, point 3. So this is inlet, this is outlet. Okay, so this theorem, okay, all this theorem, okay, this is the RTT, Renault transport theorem, can be used to solve for many kinds of multiple inlet and outlet as well. Okay, I think maybe today we stop until here. Okay, and we continue by tomorrow. Okay, for those have any question, feel free to let me know. Okay, you can WhatsApp me if you have any question pertaining to the lecture. Alright, so after this I'm going to open the assignment 3. I hope you can do it before tonight. Okay, this is the agenda. Okay, anyone? Okay, any question before we end our session?
Sir,